Hello, my name is Colva Roney-Dougal. I'm Professor of Pure Maths at the University of St Andrews.
And I'm Martin Liebeck, Professor at Imperial College, London. Right, so our programme focuses largely on the theory of groups, so I'll briefly say a little bit about those and then talk about some of the themes that we're going to focus on. So groups are defined as abstract mathematical structures satisfying some axioms, but they occur in nature in a wide variety of contexts. So every physical object in 2 or 3 dimensions has a group of symmetries. So for example, in 2 dimensions a square has 4 rotation symmetries and 4 reflection symmetries, and each of these can be described in terms of transformations of 2-dimensional space, or 2x2 matrices. Similarly, in 3 dimensions, physical objects have 3-dimensional symmetry groups, but symmetry groups occur in all sorts of other contexts, in topology, number theory, model theory, combinatorics, and because of this, group theory has many applications in other areas of maths and also in the sciences. So in our programme we're going to focus on 4 themes, which I'll briefly describe now. So the first theme is what we call simple groups. So groups can be huge, very complicated mathematical abstract structures, but there are certain special kinds of groups called simple groups, which are every at least finite group is built out of in roughly the same way that every number is built out of its prime factors. And now there was a huge theorem, one of the hugest theorems of the 20th century, was the classification of all the finite simple groups. The final step was actually achieved in 2004, but this has become a huge tool to be used both within group theory and in all its applications. And because they're so fundamental, one wants to study all sorts of properties of the finite simple groups, properties like their structure, their subgroups, and their representations. So this is one of our main focuses, and we're having actually our last workshop is devoted to simple groups, their representations and their applications. So I use this word representations, that's our kind of second theme. Representation theory of groups is a huge subject which studies the way that groups can be represented as in terms of matrices. So I mentioned all these applications of all these examples of groups at the beginning, defined as 2x2 or 3x3 or much larger groups of matrices. Representation theory is about the general theory of how you represent abstract groups in terms of matrices, and it's a vast subject with lots of connections and applications, and it's a very exciting time for the subject because there are old conjectures, some of them 50 years old plus, which have lain unsolved for 50 years, and some of them are now kind of starting to be attacked, and 1 or 2 have actually been proved quite recently, mainly because of the influence of the classification of simple groups. So that's one of our main themes. In fact, our 4th workshop is devoted to the conjectures, they are called the counting conjectures in representation theory, and we have many participants in this program who are the world leaders in this field. So that's one of our themes. Another theme is computational aspects of group theory. So computation is a huge and growing tool, if you like, in algebra, and particularly in group theory. One can kind of test and form conjectures using computations. One can prove special cases of theorems and get even ideas how to do general proofs from computation. And there's a big interplay between the current field of designing algorithms in algebra and the theory of simple groups and representations that I've been talking about. So computation is a big theme for us, and that's one of our workshops. In fact, next week, second workshop is devoted to computational aspects of group theory. And the final theme, I should mention, is applications of group theory, of which there are many, as I've mentioned, in number theory, algebraic geometry, probability, combinatorics, lots and lots of applications, and we have many participants who are experts in that field. So that's a brief, perhaps not so brief, overview of our workshop.
I think it's timely and exciting for several reasons. One of them I think Martin's already touched on briefly. So these counting conjectures, the theme of our fourth workshop, have been around for 50 years now, and just in the past 5 or 10 years there's suddenly started being major progress on them, and even in the last 2 or 3 years things are happening. So there's been the original questions to do with the counting conjectures concern all groups, and then one after quite a lot of work there have been some reduction theorems which have pulled them back to proving similar but slightly more complicated statements than the original conjectures, but now about some classes of groups which are simple groups, as Martin's already talked about, but also some groups that are very closely related to the simple groups. And there's a sense now that, particularly with this programme, we've gathered together enough of the experts in the field that there's a real chance that one of them might fall during the next 6 months, which would be awesome if that came out. Yeah. Another thing which happened a couple of years ago, which relates particularly to my own research, so I think I was going to talk about that. And this is in the thing to do with connections between the classification of finite simple groups and computation, is an outstanding problem in theoretical computer science, which has been around for ages, called the graph isomorphism problem. So this is where you're given 2 graphs, so that's collections of vertices and edges, so not graphs in the sense of x, y, but graphs in the sense of dots and lines between them, and you're asked to design an algorithm to see if those 2 graphs are the same. So technical language is, are they isomorphic? Now, building on some quite deep theory to do with the classification of finite simple groups, there was a major breakthrough just in 2018 showing that, so this problem was one of the ones where we have no polynomial time solution for it. So there's nothing that runs in time polynomial in the number of vertices of the graphs that will definitely give you a yes or no answer. And people have always wondered whether maybe there is a polynomial time solution. And just recently, there's been some dramatic progress which showed that in fact there's a quasi-polynomial solution. So that means you can do it in time bounded by something of the form 2 to the power of log to the power of something, where we're talking about the number of vertices in the graph. So it's take the number of vertices, take log of that number of vertices, raise it to a power, and then raise the answer to a power of 2, and that will be an upper bound on the amount of time it's going to take to solve the problem. There are many questions related to graph isomorphism when now we're wondering whether, again, using deep results about the classification of finite simple groups, it might be possible to pull them down from an exponential worst case bound to maybe another quasi-polynomial worst case bound. And yeah, that's certainly one of the things that feels particularly timely to me. Well, as Martin's described, our program's actually split into lots of different themes, so it's not like I can give you a single question that we're trying to address, but I think everything in the end comes back to this classification of finite simple groups. So we know the names of all of the simple groups, but trying to understand more about the structure of the simple groups and the ways in which they can behave. So by the structure we might be talking about objects inside them, so conjugacy classes or the subgroup structure. By the ways in which they can behave, I mean not just the representation theory, but also stuff to do with cohomology and related questions like that. And then how can we use the knowledge of that structure to solve all sorts of problems that are not immediately to do with group and representation theory, but are pulling out into algebraic geometry or number theory or combinatorics. Right,
well, as I said in the first question, this is one of our main themes, the applications of group theory and the theory we're covering during the programme. And as I said, there are applications in many diverse areas. So maybe I'll just choose a couple to say a few words about. So one of the very recent developments has been in the field of algebraic geometry. So if you take a finite group of complex matrices, say 2 by 2 or 5 by 5 complex matrices, but it's a finite group, then you can form what's called the quotient of this complex space by the group. So that's the orbit space for the group, and that becomes an algebraic variety. And many interesting algebraic varieties arise in this way. So usually these varieties are what we call singular varieties, and algebraic geometers very like to do what's called resolution of singularities. So this goes right back to Newton, and Riemann defined Riemann surfaces for precisely this purpose. But if you take a complicated singular variety, there's a huge theory behind whether you can resolve the singularities or not. And so these recent developments are using the structure of our finite group that we start with, properties of it, to determine whether we can resolve the singularities and if we can do it in a nice smooth way, things like that. So there are many recent theorems, and it's an ongoing field linking finite group theory with a mainstream topic in algebraic geometry. So that's the first application I was going to mention. The second one is a much kind of more classical, but still ongoing one in the field of probability. So this is relationship between group theory, representation theory, and random walks in probability. And this goes back to the theory of card shuffling. So one can think of shuffling cards. Suppose you have a pack of cards and you want to mix them up by shuffling them in some random way. So the simplest shuffle is just pick 2 cards at random and swap them around, and then keep doing it. And the question arises, how many times should I do this before I'm pretty sure the pack is mixed up? So if one thinks of each shuffle as, so we're changing the order of the cards, so we're doing some kind of permutation on the cards. So each shuffle is just a random, in this case, transposition in the symmetric group, the group of all permutations of the cards. And this question of how many shuffles do I have to do to mix up the cards, that links up with group theory and representation theory, and there are many many questions of this sort. Random walks on groups is a huge subject, and we have Percy Diaconis, who's kind of the man who initiated all this theory. He's coming for two stays, and we have several other experts who are involved in these.
I should mention Cheryl Prager, who's our distinguished Kirk Fellow, is going to be giving a public lecture, I believe, on particularly the maths of shuffling, ways in which that relates to nice questions in group theory while she's here.
Yeah. I'd like to elaborate a little bit on the applications side of things. So, as I mentioned, group theory has applications in algebraic geometry, number theory, combinatorics, theoretical computer science, and so on. And we're having a special workshop on applications. It's the third workshop, where many very distinguished world experts on a range of these fields will be coming and talking about these applications. We have I have a list of distinguished people. We have Percy Diaconis, who I've already mentioned. We have Nick Katz from Princeton. We have Professor Ngo, the Fields Medalist from Chicago, among many others. And so there's a lot of hope for some impact on the application side. And although it's within the programme, and as Colva said, these conjectures in representation theory, we have high hopes that there'll be some exciting progress on those during the programme. There are many of the world's experts on that field who will be here for substantial periods. Okay.
Sounds good.
Right.